brilliant introduction. Yep, I wouldn't have been able to explain what I do better than the way you did. So that was that was very nice. Hello, everybody. Thanks for joining us today. It's just like 2 words of warning. It's going to be quite intense in the sense that we have to cover a lot, but I'm hoping that with this, with this workshop, you get sort of a general idea of how to conduct Bayesian linear models using R. But of course, there will be a lot of things that will be left sort of unsaid. But hopefully this should give you like a basic understanding so that you can actually do, you would be able to follow more tutorials, like written tutorials, for example. So yeah, just as a warning, I'm not going to be able to go into all of the possible details, but hopefully this should just give you like a sort of a general overview. One other thing is that the workshop assumes familiarity with R, with linear models, for example, using packages like Elmer, and with the tidyverse packages. The tidyverse packages are not necessarily like that important, but definitely understanding how linear models work, it's fundamental, because I'm not going to have the time, alas, to go through the basics of linear models. The workshops focuses on linear models done within a Bayesian framework. So the main workings of linear models, as you know them from Elmer, for example, LME4, it's the same. It's just that we're going to give it a Bayesian spin. But then most of the basic aspects that you have to deal with when running models with LME4 will apply also to Bayesian linear models. So this will be an introduction to Bayesian inference, but it will focus on Bayesian linear models. As for questions, so ideally, I should probably say this first, if you manage to download the starter kit, you can actually follow along using the R Markdown file from day 1. I copied basically the code that generated the slides, so you should be able to run things while I talk about them. So the idea is that we're going to do about 45 minutes and then like a 10-15 minute break and then other 45 minutes. But I will add time within those 45 minutes for questions. If you do have like sort of a technical question related to running the code, perhaps the code doesn't work, do feel free to post questions in the chat. As Max said, he will monitor that and let me know if there's anything that doesn't work. I'm not going to be able to help you today with problems installing packages, or if the packages themselves don't work, because generally it becomes quite complicated. But if you have issues running things because they unexpectedly don't work, feel free to post a question. I'm also trying to click on chat, and apparently the screen thingy doesn't show up. Anyway, so right. So as I mentioned, we're gonna focus on linear models, and this is just a funny slide, like a Lord of the Rings reference. But the idea is that by learning linear models more generally and Bayesian linear models more specifically, you can actually model all sorts of different types of data. So they become sort of a easy to use go-to model that you can apply to a lot of different scenarios. It doesn't cover all of the possible data analysis scenarios, but most of these scenarios that as linguists we are confronted with when answering research questions that are typical of the field. Generally, linear models will be able to help you answer those particular questions. So that's why the one model to rule them all, because you can just learn the basics of Bayesian linear models and you can apply them to a lot of different contexts. And if you're wondering whether I translated model into Black speech, I did not, because unfortunately that's not a word in the dictionary of Black speech. Anyway, this one model to rule them all, as I was saying, it is the linear model. And again, you should be familiar with linear models more generally, the practical aspects of running linear models. And as I was saying, it's quite a flexible and powerful model that you can use to analyze all sorts of different data types. But what we're going to focus on in this workshop is actually Bayesian linear models. And again, they work basically, in principle, they're very similar to linear models done under a frequentist framework, which is the framework that gives you p-values. But of course, they have a Bayesian spin. And I think of Bayesian linear models as as a super power version of linear models, basically. And we're going to see why in a second. Sorry, I didn't mention the first few slides are going to be a bit conceptual, but then we're going to start actually working with our code. And you should get a more practical, hands-on type of experience in a few minutes. So usually the framework that we tend to adopt when doing data analysis, and especially inferential statistics, is the so-called null hypothesis significance testing framework. That's also called the frequentist framework or the classical framework. This is the framework that returns p-values, basically. And the output of a linear model within a frequentist framework is point estimates. So you get an estimate for an effect, for example, or for the intercept of the predictors that you have included in the model with a corresponding standard error. But this is basically the main output of the frequentist model, single point estimates and p-values related to those point estimates. On the other hand, within a Bayesian framework, the main output of a linear model is, rather than getting point estimates of different effects, intercepts, and so on, you get an entire probability distribution for those particular effects or intercepts. So rather than having just a single value, you would get a full probability distribution that you can use to say some values, for example, are more likely than others. This interpretation is the Bayesian interpretation. It's the core of doing Bayesian inference, where instead of having just a single value and knowing whether the value is significant or not, you can make claims like saying there's a 95% probability that the value lies within this particular range. Just not necessarily, it doesn't necessarily matter here, but generally there seems to be a tendency for people to interpret frequentist models using Bayesian concepts because they're much more intuitive. So in fact, Bayesian analysis tends to be much more intuitive than frequentist analysis, just because it's based on this idea of probability distributions. So this is basically the main difference between the two frameworks. In one case, you just get point estimates and p-values. In the other one, you get entire probability distributions for each predictor, for each parameter in the model. So we're going to work with a data set for the entire workshop. This is the massive auditory lexical decision task data set by Tucker et al. 2019. The original data set is massive. It's like 521 subjects. It's a lexical decision task, so they have reaction times and accuracy, whether the participant has correctly identified a word as a real word or a nonce word. But since it's so big, I decided to just basically give you a subset of the entire data set. So we will be working just with 30 subjects and a sample of 100 observations per subject. And this is what the curated, let's say, the subset of the data set looks like. You have a subject ID, you have the item, meaning the lexical item that the subjects heard. This is an auditory lexical decision task. Then it specifies whether the word, the item, is a real word or not. So you have false or true. We're gonna be looking at the von Lev column as well. That's the Levenstein distance. It's a measure of, it's similar to neighborhood density, but it's the other way around. The higher the value of the Levenstein distance, the more unique that particular word is from a phonemic, from a segmental point of view. And then you have reaction times in millisecond, accuracy, correct, incorrect, and reaction times as logs. And this is basically what the data set looks like, and what the context of the experiment that produced this data set was. So let's start with a frequentist linear model. We're gonna use the Elmer function from the LME4 package. In this case, I'm just including the Levenstein distance and whether the word that the participant has heard was a real word or a nonce word, and then an interaction between the two, plus a random a random intercept by subject. So by subject random intercept. The outcome variable is reaction times. I logged them because you might know that reaction times tend to be not distributed as a Gaussian distribution, but rather they tend to have a longer tail. And if you log them, they look a bit more normal. So that's why I logged the reaction times here, although it doesn't necessarily matter at this stage. And this is the output of the summary, of the model that we have just run. This should all be familiar to you if you have used Elmer before. And you have your results here in the fixed effects. As you can see here, you're not getting p-values because I haven't loaded the Elmer test package, but never mind that. And this seems to have worked, and this is, answer to the question of whether Levenstein distance and whether the word was a real word or not affects the reaction times. But some of you might have noticed that perhaps it's not sufficient to just include a bi-subject random intercept. Again and again, now we try to recommend researchers to not only include a random intercept, but also to include a random slopes for the predictors that you include in the model. I'm not going to go into the details of why you want to do that, but that's generally the most up-to-date recommendation, although philosophies might and schools might differ. But and this is just the plot that sort of visualizes the output of the model. You see that there's a positive correlation between Levenstein distance and reaction times. And there's also a difference between whether the word is a real word or a nonce word. But again, the results per se don't really matter. And as I was saying, it would be best to include at least random slopes for the two predictors. Ideally, you would also want to include random slopes for the interaction between these two. But if you go ahead and try it yourself and run the code in the day one R Markdown file, you will very likely see that you get a warning of non-convergence. So it will say model failed to converge. When that happens, that means that you should not in any way, in any case, interpret or use the summary of the model. It just means that the model failed to compute all of the parameters. So basically the summary will be uninterpretable. And I'm sure that at least once, that most of you at least once had this issue where you would get a model failed to converge warning And what you would do is that you would drop the random slopes and fit a model just with a random intercept. This is problematic for the reasons that I was mentioning before. We tend to recommend to include also random slopes. This becomes very quickly impossible to do within a frequentist framework because of this issue that sometimes the model just basically the math behind the model is so complicated and there's not enough data to be able to solve that math that the model just fails to converge. So this is one of the practical reasons for why you might want to move from a frequentist framework to a Bayesian framework, because we're going to see that models, linear models within a Bayesian framework, they always converge. That's one of the nice aspects of Bayesian linear models, is that you will never have convergence failure. They will always converge. They will always give you an answer. You will see though that the answer might be quite uncertain. There might be a lot of uncertainty in the estimated effects, for example, but that will still be an answer. While with a frequentist linear model, for example, you will simply not be able to get an answer for this model, and you have to simplify the model, not because it makes sense from a conceptual or theoretical point of view, but just because practically you cannot run that particular model. Right, so what we can do is that we can just go Bayesian. And I'm going to give you first sort of an overview of how that works, and then we're going to go into the details throughout the workshop today. So don't worry to try and understand everything that goes on in the next slides. Hopefully by the end of today, you should be able to understand what I was doing from this slide on. But it's fine if it's not, if you don't have a complete picture of what the following slides will be dealing with. So we can run a Bayesian linear model. It's actually quite nice. You just literally have to change the function. Instead of using the Elmer function, you use BRM. That's from the BRMS package. That stands for Bayesian regression models. And that is the package that provides the user with the BRM function. And BRM, you can think of BRM as the Bayesian equivalent of LMER, basically. Just a very brief introduction on what is the software that is actually run when you do Bayesian linear models with R. There's quite a lot of software involved. That's why you had to install quite a lot of extra software. And basically what BRM does is that it uses the same syntax that you would use in Elmer or LME4. You can see that the syntax for the model is exactly the same. And then basically it converts that syntax into the syntax of Stan, which is the software that actually runs the Bayesian models. That's all done under the hood. You don't have to know Stan. You don't have to even know that it's actually Stan that is running the model per se. And so the experience from a R user perspective, it's very seamless. You just run things in R and everything gets converted for you, and you can just check the output there. So as I was saying here, I've literally just changed LMER to BRM. And the only other difference, which is not related to this model being Bayesian, is that instead of logging the outcome, the response, reaction times, I'm specifying the log normal family for reaction times. It's just the same thing. BRM tends to be much more flexible than Elmer, so you can actually tell the model that reaction times are distributed according to a log normal distribution rather than a normal distribution. But for the purposes of understanding how a Bayesian linear model works, this doesn't really matter for the time being. So as you can see, I literally just changed LMER to BRM. That's all that you have to do to run your first linear model, basically. This is the output, and sorry, let me just check that we're gonna do, yes. So if you try to run things, you might see things happening. I'll explain everything in a second. So for now, you can just focus on understanding what happens when you actually, after you run the model. This is what the model output would look like. You see that you have population level effects. That's the equivalent of the fixed effects in the LME4 models. And the group level effects would be the random effects. And then you have all sorts of other pieces of information about the model. We're going to look into those later. But basically, most of you will be interested in looking at what happens here in the population level effects and perhaps in the group level effects. And this might look slightly familiar as well if you're used to the LME4 output. You get sort of very similar information plus information that is specific to Bayesian models, and we're going to talk about those later. And this is the plot of the model, quite similar to what we saw before, but this time we also included a random slope, 2 random slopes actually, for is word and Levenshtein distance. And the model, as you can see, sorry, I didn't mention it, the model ran fine, it converged, and I could, check the results and plot them as well. So no problem whatsoever when you run a Bayesian linear model. So let's start small. Let's go back to a simple model, and you can start actually running the code yourself if you wish. Again, here we're just using the BRM function for Bayesian regression model. And this time I'm just doing reaction times as a function of is word, so whether the word was a real word or not. And family, again, I'm using the log normal family to tell BRM that reaction times are distributed according to a log normal distribution. And these lines are more technical. This first line basically just says use the CMD stan-R package to convert BRM syntax into stan syntax. There are 2 main backends. One is CMD stan-R and the other one is R-stan. They both do the same thing, but CMD stan-R tends to be less fussy about things, and it's slightly quicker than R-stan. So that's why we're using this for this workshop. But again, this is just a technicality. Just remember that you have to include backhand equals CMD stan-R. For this to work, you have to have successfully installed CMD stan-R based on the instructions that I gave. And this second line instead simply saves the model output to a file. You just give it a path and the name of the file, and the model is saved to that particular file. And this is helpful because if you have tried to run this model, you will see that things get printed in the console or in the RMD file, and you might have also noticed that it takes some time for the model to run. This is a fairly simple model, and it's a small data set, which means that it might not take a long time, perhaps less than a minute. Depending on how powerful your computer is, it might take longer or less. And you have, immediately stumbled on one of the things that are very different from when you run LME models, is that it takes longer for the model to actually estimate all of the parameters and reach a final model output. And that is because the model under the hood is using simulations based on the data to try and estimate all of the parameters. And this is another big difference, which is more technical rather than conceptual, between frequentist models and Bayesian models. With frequentist models, what the model is trying to do is trying to solve equations based on the predictors that you have included in the model. And sometimes the equations are so complex and there's not enough data that the model simply says, no, I don't have enough data to be able to solve all of these equations. Bayesian models, on the other hand, they circumvent this issue of trying to solve very complicated equation by sampling from the data multiple times with multiple iterations across multiple chains. And I'll explain what this means just in a second. But basically, when you run the model, what happens is that under the hood, the model is sampling from the data, trying to estimate things, and that takes some time. But the nice thing about that is that by using simulations rather than trying to solve equation, you get an answer even for very complex models, right? It just takes longer, but then you do get an answer. And if you have tried to run the model, you might have seen mentioned MCMC stuff. And CMC stands for Markov chain, Monte Carlo simulations. And Monte Carlo simulations is, if you're familiar with machine learning, is a way of randomly sampling data. And the Markov chain part is a specific algorithm related to how you randomly sample from the data. All of this actually doesn't matter for the purposes of understanding Bayesian models, how to use them and how to interpret them. If you are interested, I can point you, after the workshop, I can point you to more technical readings. But again, it's not necessary to know exactly what this is. It's simply basically sampling from the data to try and get an answer for the model. There are different algorithms that can be used to randomly sample, even within the Markov chain part of the Monte Carlo simulation. And BRM uses one particular algorithm that it's thought to be the best in terms of balancing the time that it needs to estimate parameters and also the accuracy of the parameters. But again, these are just technicalities, and unless you have an interest in machine learning, it doesn't really matter to understand what this is. I did have a link to a website that shows in practice what MCMC does, but for the sake of time, I'm just going to skip it. But you can actually click on the if you're looking at the slides, you can click on this. It's a link, and it's going to show you a website that you can play around with. But again, basically, when you run the model, just know that there are simulations, there's drawing from the data involved, and it doesn't matter to understand precisely the ins and outs of that process. It's just a way of getting an answer based on the model that you're running. Right, so what we have here is just a more detailed code of what we've seen before. You have, again, the BRM function. RT has a function of is word, the data, family equals log normal, backend equals CMD stan R. I'm saving the output to a file so that the next time you run this code, it doesn't do the MCMC again. It just reads the output straight from the model, which is quite convenient. So I do recommend when you do analysis to always save the output to a file. And then these are other technical things. So I was saying that there's simulations or sampling being done by the model, and you have a lot of iterations. By default, there are 2,000 iterations, meaning that the data is sampled 2,000 times. And this 2,000 iterations are done in 4 chains so that basically you have 2000 iterations times 4. So you would start sampling things and then keep sampling until you get to 2000 iteration, then everything starts from scratch, you sample again, and you do that 4 times. So that's what the chains basically are. It's just going through those 2000 iterations of the sampling 4 times, where each chain is completely independent from the other. So if you have a computer that has more than 2 cores, you can actually specify the number of cores to use so that the chains can be run in parallel. So if you don't specify cores, the model is going to run the first chain, then the second, third, and fourth, and that will take longer than running them in parallel. It's not going to be a fourth of the time, because of course you're running 4 things in parallel, but it's going to save time. You can find out how many cores your laptop has with parallel column detect cores. That will print out the number of cores, and you can use that number as the number of cores here. If you have more than 4 cores, it's not going to matter whether you use 4, 5, 6, or 8. Because you have 4 chains, so you can only run 4 chains in parallel. If you have 2 cores, it's going to run 2 chains in parallel and then 2 other chains of the MC-MC chains. But again, this is the technical bit that doesn't necessarily, it's not necessarily relevant to being able to interpret the output. Which is exactly my next slide. How do we interpret the output summary? And that's just a plot. So hopefully you managed to run everything. Everything runs smoothly. Then you can just get the summary of the model. You can either use the summary function as you would with Elmer, or you can just use the name of the model will work as well. So the first thing tells you what the family of probability distribution the model used. In this case, it was a log normal family. And this is information about the link functions. If you know what they are, great. If you don't, doesn't matter. Then you have the formula, which is the formula that we used in the model, and the data. It says that there are 3,000 observations. And then you have information about the draws, about the MC-MC stuff, basically. It says that it used 4 chains. Each chain had 2,000 iterations. Never mind warm-up thing and total post-warm-up draws. It doesn't really matter. But this is just a general information about the technical aspects of the model. Then you have the important bit, which is the population level effects. And as you might expect, you get an intercept and then a coefficient for when is word is false, right? Is word is coded with treatment contrasts by default. So true is the reference level and false is the level that is compared to the reference level. What matters here is that you get an estimate and an estimated error. And this might look, the same, and it might look very familiar. It might look the same as with what you would get with LM-E4. And in fact, it is basically, you can think of these as the same things that you would get from Elmer. But what really matters is that these are just summary measures of an entire distribution of values. And you don't get the entire distribution here. We're going to see a plot in a second, but you get the 95% credible intervals. So credible intervals, or Bayesian credible intervals, I'm sorry, I just need to check the time. Bayesian credible intervals are what most people think confidence intervals are. There's a tendency of interpreting confidence intervals as there's a 95% probability that the value falls within the range. That's unfortunately not what frequentist confidence intervals are, but it's definitely what credible intervals, Bayesian credible intervals are. That's why I was saying that Bayesian is actually much more intuitive, because in fact, some of the interpretation that you would apply to Bayesian is the interpretation that is unfortunately wrongly applied to frequentist models. So what this column is telling us is that there's a 95% probability that the intercept value is between 6.83 and 6.86. It's a very, very narrow credible interval. I'm sure you agree with me. It's just a difference of 0.03 log odds. I didn't mention it since we're using a log normal distribution. These are log odds. And in fact, the certainty around the intercept is quite high, right? It's a teeny tiny, it's a very narrow credible interval. So in fact, what you should focus on when you look at the output summary is the credible intervals rather than necessarily the estimates and the estimated error. The credible interval matters much more than the point estimate, because that's exactly the point of doing Bayesian. You get a full distribution of values, not just a point estimate. This happens to be the mean of the distribution that gives you this particular 95% credible interval, but we're going to see this in more details in a second. So the intercept is the reaction times when the word is a real word. What happens when the word is not a real word? You actually increase the reaction times, and according to the credible intervals, you increase it by a value that is between 0.1 and 0.14 at 95% probability. You can also say at 95% credibility or certainty as well. They're all equivalent. So again, here we are quite certain about this particular result. You get an increase that is between 0.1 and 0.14. And that's it, really. That's the most important bit about the summary. And I'll just going to briefly talk about other things. One is the R hat value. This is a measure of convergence. It needs to be as close to 1 as possible. When it's above 1.5, for example, it means that the model hasn't completely converged. And you might say you lied to us because you said that they always do. They always do. Sometimes they don't do the first time, but then you can add some iterations, for example. Instead of doing 2,000, you do 4,000 iterations, and that generally helps the model converging. There are other tricks that you can use, but the idea is that maybe by doing a few extra tricks, then the model converges. In many cases with complex models in the frequentist framework, you can try all of the tricks you want, the model will not converge, basically. But you don't really have to worry about this, because when you run the model, it's going to warn you if the R hat value is not good. So you don't have to make the judgment yourself. The model will warn you. It will say some R hat values are higher than 1, and you might want to increase iterations or use different parameters. And it tends to be quite informative. It tends to help you as to what you can do to get a hat value that is better. The bulk. Yes. No. The bulk.
Yeah. Sorry.
Yeah. It's right.
Is it okay? I have a couple of questions from
Go ahead. Yes.
From people, and I thought they would be quite related. So one is actually just related to what you were saying. And the question really is like, how do we get to the value for the chains and iterations that we decided earlier? So I think you just covered the iteration one now that we can increase to 8 convergence. Is there something else we should know? How do we decide whether we want 4 or more of the chains?
Yeah, so that's a good question. So in general, 2000 iterations are enough. That's also the default. So when you run when you run BRM without specifying iterations, 2000 are used by default. And for most models, that will be sufficient. If you get warnings about the model not having converged well, then you can increase them, and you can try, to increase them by 1,000. And then if it doesn't work, you try again. The number of iterations doesn't have any effect on the model output, meaning that it's just going to affect the ability of the model to reach an answer, but the answer is going to be independent from the number of iterations. Generally, the less data you have and the more complex the model is, the more iterations you need. But what I do generally is I just start with 2000, and then I see if I need to increase them. There are other parameters, I'm not going to discuss them, but there are other parameters that you can also fiddle with if you have convergence issues. But generally the documentation is quite well written in that sense. So yeah, basically just start with 2000, which is the default, and if you need more, you just add more. These are really how can I explain this? Like this, it's about the computation, not about the stats, if it makes sense, hopefully.
Yeah, and sorry, another quick question about the how would you go about setting the seed for reproducibility of the results? You just use set seed as you would for Bayesian, but also you mentioned saving the model, I guess, is also
So that's a very good question as well. There's actually a seed argument in BRM. So you can specify a seed within the BRM function, or you can do it as you would with set.seed in R. It's just the same. And that's a good question in the sense that since the sampling is random, every time you rerun the model, the sampling will not be exactly the same, meaning that you might get slightly different values. Generally, the difference is like in very small decimals, so you wouldn't notice, but you can make it reproducible by specifying the seed either directly in the function or in the script, for example. Yeah.
Perfect. That's all the questions for now. We have some more questions later.
Great.
I think, but less time sensitive.
We could actually have the break now. Yes. Yeah. Let's do this. I'm actually happy to. What should we do? Like, I can answer some questions now, and then we can take the break, perhaps. Since we're here, good. Or should we have the? Yeah, let's do that then. Sorry, I'm just going to stop sharing here, and that's where the chat was. Okay, I just noticed that. Right.
So you can either raise your hand or type in the chat. I will keep the recording on. I think it's nice to include questions for people watching this later. So you can just type. Yeah. So we do have a question from Winnie.
Hi, thanks. You were explaining what bulk ESS and tail ESS were. Could you just finish that explanation? Thanks.
Yes, so that's related to the estimated sample size based on the draws done by the MCMCs, the MCMC chains. So that will not be the same as the sample size, as the actual sample size of the data, right? Because it's based on the MCMC. And again, it needs to be enough. There is no absolute value that makes you say, okay, it's enough. But again, the function will tell you whether the bulk estimated sample size and tail sample sizes are not high enough. So basically, the model will tell you there hasn't been enough sample sizes to estimate things. And that's generally also related to getting an R hat value that is greater than 1, basically. So again, you don't have to worry yourself. The model will warn you if it thinks that the sample size was not big enough. And what you can do is that you can increase, again, iterations, and there are other tricks that we're going to see tomorrow because they're related to setting priors, which we'll talk about tomorrow, actually. So yeah, that's basically it. But if you are interested in understanding more, again, like I strongly recommend looking at the documentation of BRM, because it's written quite clearly, and it gives you a little bit more explanation.
We have another question in the chat about so whether we can specify a parameter in BRM to change from 95 to, for example, 99%.
Yes, you can do that. You can do that in the summary. So as I said, there are two ways. You can either just type the name of the model, the variable that you set the model in, and then you get the output, or you can use the summary function. And I think it's the prob argument. So if you do something like summary model prob equals 0.6, I think that should give you a different credible interval. So for example, 99 instead of 95, or in this case, 60%. Yes, I never quite do it. So because then I get the credible intervals myself manually, and I never quite remember if it's prob or prob.level, but the documentation should say that, but that's how you do it. Yeah. And you would get different credible intervals. In fact, since we mentioned this, I do recommend actually getting multiple levels of credible intervals, not just the 95. And apparently, thanks, people are confirming it's prob. So the fact that the default is 95 is because of frequentist, the frequentist framework, where you have the 95 level, or the 0.05 alpha level. But that's, you could use any number. You could use 60, 70, 80, and 90. And in fact, I do recommend when getting credible intervals, we'll see more about this when we look at the outputs, at the plots. I do recommend getting, 95, 85, and 75, for example, because you can literally interpret them as there is a 75% probability that the value is within this range. And of course, the lower the probability, the narrower the range, which is great. It means that there's just, more certainty about the estimate, but lower probability that that's actually the case, right? And that is basically a conservative approach. So with a 95% probability, you have a high probability that the value is within the range, but the range is larger, basically. So it balances out uncertainty and probability of getting that particular value.
We have another question by Paulo, who asks, in LMEM, you would usually use sum to zero contrast to get interpretable outputs. Does this also work in BRM models, and is it advisable?
Yeah, so anything that works in terms of contrasts, in terms of coding contrasts for discrete predictors or factors, you can use exactly the same functions that you would for ELMA, and that's up to you whether you want to use sum coding versus treatment coding or other coding. It's not going to change the final the final result, which is you will find an effect of increasing or decreasing. It just doesn't matter. My experience is that since it's much easier to extract information from, it's more involved to extract information from Bayesian models, but it's easy. Once you get that information, it's much easier to get answers that you would generally get by using sum coding, for example. So when you want to get, for example, an intercept that is the grand mean, You can do all that by hand after you get the model output by extracting the posterior distributions. We're going to talk about that more after the break. So that's up to you. But if you're used to work with some coding, then you can keep doing that, and it's just not gonna matter in terms of getting the model to run. Yes, sorry, Max, I just read the question and I'm just going to answer it. Yes, so exactly. If you're using, if you're running a Bayesian logistic regression, it works exactly the same as a frequentist logistic regression, but it's just Bayesian. So you will still get log odds. That's why I'm saying, like, it literally, the main aspects that you know from running models in LME4, they apply to Bayesian models as well. So running a logistic regression, you would actually specify, that's a bit tangential, but when you specify family equals binomial, using GLM or GLME4, in fact, in most cases, it's using a Bernoulli distribution rather than a binomial one. And it's done without you noticing. So if you want to run a logistic regression in Bayesian, with a Bayesian model, you would use the Bernoulli family rather than the binomial family. But I don't remember. I think we might see a logistic regression tomorrow. But again, then yes, the output will still be in log odds.
Okay, should we take a break now? And
yeah,
come back maybe in 5 minutes, or you say something?
Should we do 10 perhaps? Should
sure.
we get back? Yeah. So now here it's 2 p.m. So we can do 10 plus 2. So whatever time is that you're at, about 10, 13 minutes from now, and we can go on.
Okay, I'll pause the video. Please do remind me later to start again. I will forget.
Yes. I will as well.
Okay, we're back. I did resume the recording. So yeah, 10 past 3 here. Happy to start whenever you want.
Yeah, so I'm seeing a few people having issues with CMD stan R. In theory, when you install CMD stan R with the install underscore CMD stan R function, that should set everything for you. If that has worked fine, then the best thing to do is to close RStudio and reopen it, and that should have all of the paths set correctly. If not, it very much depends on your setup, especially if you're using laptops that are managed by your institution, like your university. I had people in the past having issues just because the read and write permission weren't like exactly the ones needed for everything to run smoothly. So you can try, sorry, it's install CMD stan without the R. You can try and rerun install underscore and CMD stan, and that might fix things, hopefully. I'm sorry if not. One thing I didn't mention, which I will briefly mention here, is that it's a bit of a bummer to set everything up, but once it's set up, then it's going to work unless you update R or your operating system. Then at that stage, you have to reinstall everything. But alas, that's the cost of being able to run very, very complex models. You need a lot of pieces of software. But generally, once you set it up, things should just work. Great. So let me just share my screen. Okay, there we go. Yeah, so
the recording needs to be restarted.
We did already. Yeah. It should be Max. Do you start the recording?
It
Yes.
is recording. Yes, thank you.
Yeah.
Never mind me, sorry.
It's all right, thanks. Considering how likely it is that I forget and Max forgets as well, I think it's always good to double check. That's what we've seen so far. That's really it for the for interpreting the output summary. You just look at the credible intervals for the different predictors. Never mind the family-specific parameters, doesn't matter for the time being. And then the last bit just literally tells you what the bulk ESS and tail ESS are, and that convergence, the R hat value has to be 1, but that's basically it. Sorry, let me just check. Yeah. Great. So you can also quickly plot the results of the model by using the plot function. And what this does, it plots for each of the parameters in the model or estimates in the model, it plots the entire probability distribution of that parameter. In this case, we have 3 parameters: the intercept, the parameter for is word equals false, and then the sigma parameter, which is basically the standard deviation of reaction times once you have accounted for the intercept and word false. For most things we do, we tend not to look at sigma in this case, but it's there just for completeness. What you see here are exactly the probability distributions of, let's just focus on the intercept and is word, the probability distributions of these 2 parameters. You see that on the left side of this plot. And on the right side of the plot, you see diagnostic plots for the MC chains. I'll talk about this in a second. Just focusing on the left side of the plot, these are probability distributions, as you know them. And these are called in the Bayesian framework, these are called posterior probability distributions because they come after, post having run the model. So from now on, I will be talking about posterior probability distribution, or just posterior probability, or just posterior. They just mean all the same thing. It's the entire predicted probability distribution of the parameters. We'll see why it's called posterior tomorrow. It's because it combines the priors, which I'm sure you must have heard of and you're very curious about, but we'll talk about those tomorrow. It combines priors and data together to give you a posterior, which is what you see basically in this particular plot. So just to reiterate, the output of a Bayesian model is an entire probability distribution, also known as posterior probability distribution. You get 1 per parameter in the model. And when you combine all of those posterior distributions together from all of the parameters, you would get the joint posterior distribution, which is basically the predicted distribution of the outcome variable. We'll see that in a second. If you want to get the parameters or variables in the model, you can use the variables function. This is helpful later on, but I just put it here for completeness sake, but it doesn't really matter. And what you can do quite easily is to extract the draws of the MC chains. So you can actually see for each chain, you see here for each chain, this is chain 1, and for each iteration within each chain, you see what is the value that the that specific iteration has picked for the different variables or the different parameters. And this is the value for the intercept. So that is what happens basically under the hood. For each iteration, a value for each parameter in the model is picked by the MCMC process, and then you get to a new iteration, a new values are picked, and so on and so forth. And by the end of all of these chains, you get basically a list of parameters, a list of values for each parameter in the model. And you can extract all of those values with the gather draws function. This is just a short form to extract all of the variables that start with B underscore. And as you can see here, there are only two variables in the model that start with B underscore. That stands for beta coefficient, if you're familiar with that way of looking at models. Otherwise, again, it doesn't really matter. And you can get the values that were picked during the MCMC chains by using the gather draws function. And now you just see the intercept here because that's what you get at the beginning of the of this output. But then there will also be the B underscore is word false. And basically, by getting the draws, then you can plot things any way you like. So that's why it's very flexible. And I was mentioning this before, that once you know how to get the draws out of the model, then you can do whatever you want with them. You can calculate means and standard deviations. You can plot them in different ways. And I'll show you briefly what you can do actually with this and what you can plot. Using, again, the gather draws function and ggplot. So you can simply use ggplot to actually draw things, to plot things from the model. So what I'm doing here is I'm just extracting the values that were picked during the MCMC chains for the intercept. The name of the variable in the model is B underscore intercept. So that's what I'm getting. And then I'm just piping everything in ggplot, and I'm just plotting whatever has been output by gathered draws. I'm not going to go into the details of ggplot because it's not really about Bayesian. It's more about ggplot. But this is basically the output. What I'm plotting here is the density distribution, the posterior distribution for the intercept. And there's also a median of the entire posterior. And I think this is a 65% credible interval. And this, you don't probably see it much because it's black. And this is the 95% credible interval. If you compare this with the output of plot, you'll see that it's exactly the same. So it's just two ways of getting basically the same information. This is done automatically for you, like you just run a plot and you get all of the posterior distributions. Well, this method gives you more control as to what you want to plot and how you want to plot it. So again, this is literally this is the output of the model for the intercept. The model has estimated that the intercept value is within this particular probability distribution, right? And you can get the median, in this case, is about 6.85. These are log odds. And that's exactly what you got here. Estimate 6.85. So the estimate here, it's like the mean or the median. You can pick which one you want of the entire distribution. So that's why I was saying at the beginning, I wouldn't really focus on the estimate per se, because that's just a summary value of an entire distribution. What really matters is the entire distribution here. Because yes, the median is 6.85, but according to the model output, the value could be anywhere between this value, for example, and that value at 95% probability, right? So basically, the focus shifts from point estimates to an entire distribution. Then you can do the same with the coefficient for is word equals false. So that's basically the change relative to the intercept in reaction times when the word is a nonce word rather than a real word, right? So this is the estimate that you see here. 0.12, but that comes from an entire distribution, which is the credible interval of which is 0.1 to 0.14. And this is what you get. So this is basically plotting the predicted posterior probability, or just the posterior probability of the effect of is word when is word is false. And this is basically what you have to add or subtract to the intercept to get the actual value for when for when is word is false. Again, this is all this is exactly the same as with frequentist linear models. It's nothing new. Hopefully, you know, if you have a strong understanding of linear models, this should all be familiar, and it has nothing to do with this being Bayesian. It's just applying the same principles, basically. So you see again that the effect of is word equals false is between 0.1 and 0.13 at 95% credibility or probability, because that's the 95% credible interval. And you get the median again at 0.12, which is exactly what you saw in the model output. So again, the most important bit here is that we are not talking about individual point estimates, but about entire probability distributions. Forgot to start my clock over there. Right. So diagnostics, they're important, but they're not fundamental. But that's more my philosophy of statistics than, you know, just as something that is prescribed or proscribed. In fact, it's much more straightforward to do diagnostics with Bayesian models than with frequentist models, and I'm going to show you the most common ways of doing diagnostics for Bayesian models in the next slides. So one of the first things that you generally do is the MC chain diagnostics, and that is basically what you got when you plotted the model. Remember, on the left you saw the posterior distributions, and on the right you saw this MC chain plots. These are also called caterpillar plots because they look like a hairy caterpillar. And the idea is that these plots for each parameter have to be as hairy as possible, basically. So you want your caterpillars to be hairy. That is related to how well the chains have mixed with each other. And I'll show you what bad chains look like. So this is actually quite a, you know, it's quite a good hairy caterpillar for, sorry, this is, it's a figure that I got from the internet. It's not from models that we're running today, because believe it or not, it's very difficult to find data that leads to very bad MC chain. So I just found this on the internet. There are some issues with this. You might see here, you see that there's this sort of line where the chain wasn't really going up and down, but it was actually staying around a particular value. And you do see that here, it's marked actually that around that iterations, there were divergences. And the divergence is of this specific chain relative to all of the others. It's much clearer here. So you see that definitely this does not look like a hairy caterpillar, if anything like a half squashed hairy caterpillar, alas, very sorry for the caterpillar. And you see that here, this particular chain has diverged relative to the others, because you see that the others do this, while this one just goes flat. And you see other divergences here. Same thing here, there's a divergence there. So ideally, you would want to have a look at the plots, and you would immediately notice if there are like strong divergences like this one or this one. Again, the model warns you if there were too many divergences. And again, the way to fix that is to increase iterations or fiddle with the priors that we're going to look tomorrow. So again, it's something that is fixable. It generally just means that you have to run the model for longer, basically, but then things work out. And there is no specific value that tells you, okay, if it's above this value, then the divergences are too much. No. Again, the model will warn you if the divergences are problematic, but otherwise you are fine even with something like this. I briefly talked already about R-hat and effective sample size. That's another diagnostic that you do, and that's quite easy. You do it as soon as you get the output. You immediately see if the R-hat is 1 or higher. And again, the model will warn you if either R-hat or effective sample sizes are too high or too small. So again, you don't really have to worry about that yourself. The last thing that you can do is to use the posterior predictive checks. This is basically plotting the joint probability, the joint posterior probability distribution of the model. That is simply pulling all of the probability distributions together from each parameter to give you a final or joint probability distribution. And in this case, here we have reaction times. These are milliseconds now. The model knows that reaction times are in milliseconds, but that we used a log normal family. So the coefficients are in log odds. But when you use the pp_check function, that converts everything back into the original scale. And in this case, you have milliseconds. The dark blue density plot that you see here, that's the density plot of the data. So that is the data that you have given to the model, while the light blue ones are the probability distributions predicted by the model based on the model results. And in this case, I chose to just plot 100. You can plot 10, you can plot 50, you can plot 1,000. The more you want to plot, the longer it takes for the model to run. These are predicted probabilities based on the draws from the model. Remember that we use the gather_draws function to see for each chain, each iteration, what value the model has picked in that particular iteration. What this is doing is just selecting 100 of all of those iterations at random and then producing basically a probability distribution based on those randomly picked numbers. The idea of these type of plots is that the original distribution of the data should match as closely as possible the predicted probability of the model. You can see here that more or less it's not too bad in the sense that you get a longer tail to the left, even in the predicted light blue probability, meaning that the model has captured this idea that you have more values that are larger to the right than values that are smaller to the right. This is very common with with measurements that are bounded at 0. You cannot have negative numbers, so you would get this longer tail. So this is quite okay, but you can see that the model has sort of overestimated the probability of these values, these reaction times values here, because you can see that the original data, the probability of the original data here is lower, while the model is predicting a slightly higher probability, and vice versa here around like 1,000. The model is sort of predicting a lower probability for those values than what the actual data is. So ideally, when you look at these plots, you would want the blue line to match the light blue lines. Sometimes that is not possible. Most times when when there isn't a match, it's because there are other factors that are affecting the data that were not included in the model. And this makes perfect sense because we were just including whether the word was a real word or not in this model, but we're going to see with more complicated versions of the model that the dark blue line matches the light blue lines. Again, sometimes it's not possible to get it to match, as nicely as you wish it would. That's also fine. It's problematic when it's really, really off, when you clearly see that the light blue lines do not match the dark blue. I would say that this case that you see now on the screen is sort of midway. I would probably say that this model is not great for the data. But I'm a bit biased because I know that there are more predictors and I know that I can do better, right? It might be that in some cases, for the purposes of answering a specific question, something like this would still be okay. So unfortunately, again, there is no gold standard that you can say, okay, this is good. It's a matter of getting a model that is the best for based on the plot. But that's just about looking at the plot and seeing whether this matches the light blue lines or not. If actually might be worth mentioning this now, if you come from machine learning, for example, or if you come from a approach that uses a lot of model comparison, information criteria, methods or machine learning style like stepwise functions for selecting models, that's absolutely fine. I just don't talk about it. It's absolutely fine, and you can apply it to Bayesian models. I just don't talk about it because that's just not what I tend to use. But again, that's about preferences. Generally in my research, I have a specific research question or hypothesis that I want to test against the data. So I define a model a priori, and then I use that model, and I don't want to fiddle, trying including or excluding predictors. But again, that's just a different way of doing data analysis. So what you're seeing today and tomorrow is this idea that, you have one or two models and that's it. And then you want to learn about what the models are telling you rather than trying and find the model that best fits the data. That's a slightly different approach, but it works as well with Bayesian models.
Stefano, I think we could answer a few questions, if that's okay.
Yes, I think
we have about 3 or 4 from
that's
the past.
exactly the time, because we're going to level up next. So definitely a good time now.
So the first question is, what do you do if you see that your posterior distribution is clearly bimodal, and you don't have any other predictors than the ones you have already included?
Yes. So if when you see, can you see my screen now? Should work.
It's white for me.
Then no, just a second. Let's share the entire desktop. Okay, now you should see my slide. So if you were talking about the posterior predictive checks.
No, this was much earlier than that, actually.
Sorry again?
This is not related to this plot. It was, I think, more of a general question. Yeah, like.
Right, so it depends whether it's, so if it's about the posterior distributions of the parameters, it doesn't matter whatsoever, and it's not related in any way to whether the model is fitting the data well or not. It's just a matter of variability in how the model is sampling the parameters. So if I rerun this model, perhaps you're not going to see a bimodal distribution here, and you will see it there. It just doesn't matter. So you shouldn't worry about that. But if in the posterior predictive checks, your original data set has a bimodal distribution, and the model instead is unimodal, it might very well be that it's because there are predictors that are not included. Sometimes that's not even, it's not even about other predictors that are not included. It's about that particular sample is bimodally distributed. Maybe if you had collected a new sample, it wouldn't. In that case, it's fine if the predicted light blue ones are unimodal and the data is bimodal. You know, again, this has to be the best that it can be, but sometimes it just cannot be exactly the same as the original data. So again, that depends on the data itself rather than on, you know, trying to add or remove predictors there to account for. And it did happen to me, not very frequently, but it did happen to me once or twice where the model were clearly bimodally distributed. Sorry, the data was clearly bimodally distributed, and I couldn't find any of the predictors in the data set that could actually account for that. And at that stage, you just acknowledge it, that there seems to be, you know, a bimodally distributed aspect in the data that cannot be accounted for with a particular model.
We have a couple more questions. One is about plots, I think in general, that you've shown in the past 10 minutes. And the question is, why does the y-axis sometimes goes slightly under 40% for the slope estimates on slide 19, and sometimes all the way up over 90 for sigma, while the x-axis spread is quite similar?
I'm not sure I understand. Is it about this?
I think slide 19 is mentioned.
Yes. Oh, yes. So if it's about these, it's because these are not, these are weird. So they don't sum to one. So that's the thing. Generally, when you have density plots, you like the density sums, the density of the entire probability sums to one. This is not the case. I actually do not quite remember what these values are. It's related to the sampling of the MCMCs, but you know, it's just that, of course, these values will be more probable than the ones on the tail. But yeah, the x-axis, that depends on the actual estimates of the oh, maybe you were talking about these. If you were talking about the hairy caterpillars, these are iterations. I didn't mention it, but you run 2000, but then only the last 1000 are used. So only half of them are used to actually estimate things. The first 1000 are used to warm up the model, basically. So that's why you get 0 to 1000, but then you get different things on the y-axis. I hope that answered the question.
And the last question is about when and how would we talk about a 65% credible interval? In which case does it provide more useful information than, say, a 95% credible interval? I'm asking, given that we plot it.
Yeah, so again, I've been using 95% credible intervals just because those are commonly used. But in fact, I do recommend plotting or getting other types, and there's no set value, or there is no set of specific values that are generally used depending on whom you read. Like if you read Michael-Reith, he says just use any number. If you read Gelman, it says use like the empirical rule values, 62, 90, 62, 89 and 95, for example. It just, they tell different things. Like a 65% credible interval tells you the probability, that there is a 65% probability that the value is within that range, which is very different from 75. Sometimes I even used 40% credible intervals and 50% credible intervals. Do not think of credible intervals as at chance level. A 40% probability is still a 40% probability that the value is within that particular range. And sometimes, depending on which I wanted to convey, I would say if we look at the 95% probability, we get effects that range from -50 to +152. And if we look at the 40%, we only have positive values, for example, and that's still informative. Basically, that amounts to say that there's a 95% probability that the values are between -50 and +150. But there is a 40% probability that they're just positive. And, 40% is quite low, but it's still not 0%, right? So sometimes you might be able to say there's a 70% probability that the effect is only positive. So that's how you use these credible intervals, right? It's not, and it doesn't have anything to do with significance, right? I didn't mention it. Significance testing is just for frequentist models. It doesn't apply to Bayesian models. There is no statistical significance in Bayesian models. There's only probability of getting a value within a particular range.
That's all the questions so far. We have about 20 minutes left if you're...
Yeah.
Yeah.
Great. So, oh God, now I need to go back. Oops. Yep. So the rest is actually quite straightforward in the sense that I'm just running slightly more complicated models. Let me just reshare the right window. Right. So as I mentioned before, we just used is word, but now I'm adding Levenshtein distance and an interaction. I'm also including group level effects. Somebody has asked before, and the answer was correct. Group level effects is just what we call random effects in frequentist linear models, and population level effects is what we call fixed effects in frequentist models. So same things again. I think this was probably not intended to be there. So this is multi-threading. If you're familiar with the concept, great. If not, never mind. This is about, again, computation. Doesn't have anything to do with actually Bayesian models per se. This would only work if you have 8 cores. You specify 4 cores. So each of the 4 chain is run on 1 core, but each chain is split in 2. So you get half of the chain run on 1 core and the other half on the other at the same time. So you have 8 cores. If your computer only has 4 cores, this is not going to work. And sorry, I shouldn't have included that. But if your computer has 8 cores, you can run this and it's going to run quicker than just running 4 cores without the multi-threading. But again, doesn't really matter. This is the output. This is just the same as we had before. Family formula data draws. Nothing is really, nothing new has popped up here. Now we have the group level effects. Those are like the random effects of linear models. And what you get here is basically the same sort of, the idea is sort of the same as with population level effects. For each random intercept and random slope, or group level intercept and group level slope, you get a posterior probability distribution, an entire probability distribution, and you get the 95% credible intervals there. Again,
Stefano, sorry, we're
yeah.
still seeing the model. We're not seeing the summary. Yeah.
Just give me a sec. To zoom. Share screen. Share screen again. Okay, share. Do you see the summary now?
Yeah.
Okay, great. Sorry. So I was saying that this is what would be the random effects model in LME4. Here are called group level effects. And again, it just works the same. You don't get just a single value, but you get an entire probability distribution that is summarized by the credible intervals, in this case, 95% credible intervals. You get values for the group level intercepts and the random slopes as well. If generally we tend not to focus on group level effects, but it depends on what you're interested in. The interpretation of these is the same as with frequentist linear models, but instead of just getting a single value for the variance, for example, the variance or the standard deviation, you get an entire distribution. But again, they work exactly the same as they would in a frequentist linear model. Right, so this is the output, the model output with the conditional underscore effects function. You just give it the name of the variable you save the model in, and then you have to specify which effects you want to plot. In this case, I'm asking to plot Levenshtein distance, is-word, and the interaction between the two, and this is what you get. You see the reaction times converted back into milliseconds on the y-axis, and here we have Levenshtein distance. We see that with increasing distance, you have slower reaction times, and the reaction times are on average slower when the word is a nonce word, not surprising. And you might see that there seems to be a steeper effect of Levenshtein distance for real words than nonce words. Why that is depends on perhaps your conceptual and theoretical frameworks that you adopt. But this is just basically the what the model is predicting based on the data and the formula of the model. There's you can also so when you run this function, it plots the model, it plots the output for you automatically. You can also actually add extra arguments to the function, basically to get different styles of output. So for example, here I'm plotting a spaghetti plot. Basically what this shows you is the uncertainty around the predicted effects of Levenshtein distance and is-word. Each of this line is a possible line based on the model, right? So it shows that in fact this line could be the real line that that captures the real effect, and this one could be as well. So this is just a way of visualizing uncertainty. I didn't mention it. Sorry, these are credible intervals. The shadowed ribbons here, and you can interpret these as to mean the real value is at 95% probability within those intervals. This is not what you would do with confidence intervals from a frequentist linear model. But with a Bayesian linear model, you can say that. So you see, for example, here that there is an overlap. So, it's based on this data, it is possible that in fact, when you get to higher Levenshtein distances, there is no difference between whether the word is a real word or a nonce word. But there could be, because you see that these bits do not overlap, for example. But this again is about interpreting linear models more generally, rather than interpreting Bayesian models particularly. This is just the last bit, and then we can reconvene tomorrow. Sorry, I forgot to remove. This is a warning that doesn't matter for the purposes of this workshop. This basically is showing for each subject in the data. Remember, there were 30 subjects. I included the red dot is the original conditional mean of the intercept of reaction times. You can think of these as the average reaction times by speaker when word is true, and Levenshtein distance is 0. And the red dots are the original means from the raw data, and instead the black dots with the confidence intervals, those are the conditional means as predicted by the model. And you see that what happens when you include group level effects, aka random effects, is that the individual means shrink towards the conditional to the overall mean, and that's called shrinkage. So the main effects of random effects or group level effects, whether it's Bayesian or frequentist, is to shrink the individual parameter, the individual values of, for example, subjects or words towards the population level mean. And at the same time, the population level mean is influenced by this shrunk values. Again, I just added it here because it's easy to get this information out of the model. Basically, you can check the code in the code of the slides. And this just shows that you have shrinkage basically for the group level effects. But again, it's just an extra thing. And this is just the same plot without the red dots. So I think, yes. So we didn't talk about priors. That's definitely the hottest topic in workshops about Bayesian. It's actually easy. Once you understand how they work, it's actually easy, but they can seem counterintuitive at the beginning. And most times we will tend to use we will tend to specify priors that are so general that don't necessarily affect much the output in ways that some people are worried. Generally, the worry is, what if my priors are affecting the outcome of the model so much that in fact I'm not getting a truthful answer? I'm going to explain to you what priors are, how to specify them, and how we can specify priors that help the model settle to a particular answer, but priors that do not, confound the model, basically. So that's what we're going to be doing tomorrow. Basically, we're just going to be talking about priors and how to implement those. And I think that's all for today. If there are questions, I'm happy to answer them in the last 5 minutes. And yes. And as I said, I'm sorry, this is really intense and it's a lot to cover. The aim of this is for you to have a basic understanding so that you can actually go and, for example, read more tutorials. But for simple analysis, whatever we have done today and what we're going to do tomorrow should set you actually up for the very basic things. Then depending on your specific interests or needs, you might need to know more. But hopefully this has given you sort of a head start into how to fit Bayesian models.
Thank you so much, Stefano. We do have a couple of questions in the chat already. So one is quite long. I'm not sure whether you prefer to just read it. So by Mahmoud, I don't know if you're already on it.
Yeah. So Mahmoud was wondering what happens if you want to look at an interaction with two within interaction factors, congruent and incongruent, and silent aloud, have a between group factor, monolingual and bilingual. Yes, would basically be able to handle it. Yes, that's, it's just the same as it would with frequentist linear models. So you would have, you would use some of these predictors, for example, as population level predictors, and perhaps some others as group level predictors. It depends exactly on the study design. But yes, there's no limit as to what you can do in terms of analyzing data, as long as the design of the study makes sense, right? Sometimes we come up with designs that do not lend themselves easily to do analysis with linear models, but otherwise they generally work. So then Alan says, regarding the my subject conditional means, can you tell us whether the model captured the subject related random effects well or not? No. So it's in the sense that that's more about model fit. So to be completely sure, you would have to do model comparison. So the model wouldn't, sorry, the conditional mean wouldn't necessarily tell you whether the random whether the different participants are behaving differently and to which extent. So that's more about comparing different models with different random effects, basically. So if you get X divergent transitions after warm up, that is about the divergences in the MC-MC chains. It's fine if you have a few, even if it's, even 20% or, 10%. Again, the model will warn you if there are too many. Sometimes you don't have any divergent transitions. Sometimes you have a few and it's fine, because that's different from convergence. So sometimes you can have divergent transitions and the model has still converged. So the important bit is that it converged. When the transitions, when there are too many divergent transitions, the model warns you and it tells you you need to do something. Yes, so Bayes factors, we're not going to talk about those because of principles, really, but they are the easiest thing to understand about Bayesian analysis. It's not that I'm against Bayes factors, but they tend to be used as significance testing, which is not what Bayes analysis is about. But you're more than welcome to use Bayes factors. Basically, a Bayes factor just tells you how much. It tells you about the probability of one model over another, basically. So you can use them if you're comparing two different frameworks that have two different expectations in relation to the data. You would be able to compare them, for example, using Bayes factors. Yes, Bayes factors are the new p-value. And it's funny how now journals are saying, you can only publish things that have at least a Bayes factor of 6. I mean, it becomes a bit tricky at that stage. I am part of those people that believe that we should only base our inferences on the posteriors, and that's all, which makes things a little bit more complicated, but never mind that. Last question by Paolo, since Bayesian done up, yes. Any results? Oh yes, and yeah, that's probably, there you go, that's where the Bayes factor came in. So no, so significance is a concept that works only with frequentist statistics, not with Bayesian. So there is no significant effects in Bayesian analysis. There's just the probability of an effect being within a particular range. And there is no precise probability. For example, if you tell me that there's a 60% probability that this condition positively affects the outcome, I would take it, because 60% is already, high. If you tell me that there's a 20% probability of, a increase in performance, then I would say, well, perhaps, this is not particularly relevant for this, but it's still a result. But if you say, I can be 95% confident that based on the data and model, this particular context produces an increase in the outcome variable, then that's 90%. So basically, the reader has to be warned that it's not about whether an effect is significant or not, but it's about the probability for the effect to be of a particular value, basically. We'll probably talk about this a little bit more tomorrow when we talk about priors as well. But the main difference between frequentist and Bayesian is the mental mindset, the mindset that is completely different, rather than understanding how linear models work, basically. Yeah. So yeah, sometimes it does need a bit of convincing, and unfortunately, readers, since most of us are trained in frequentist statistics, sometimes trained with some of the common misconceptions, for example, as to what a p-value is or what a confidence interval is. Sometimes you get people trying to apply what they learn from frequentist statistics to Bayesian because they have a sense that that's the only way of doing statistics. But there are many ways, and sometimes what we try to interpret within a frequentist framework that we shouldn't actually works within a Bayesian framework. So you get a mix of things that work well because people are just doing whatever they used to do and now they're doing it correctly when they interpret things, or you're getting people that want to have a yes/no answer, yes, this effect is significant or not, that doesn't necessarily apply to Bayesian statistics. So yes, it's I could run a 1-week workshop just on this. So I'm just giving you some teasers, but I cannot go into details.
Yeah, we do have last question. I would like to ask one quick question after as well, if that's okay. But just before we forget, Adam is asking whether we can have the slides, because I think that only the R Markdown is present in the, I think he was interested in looking at this MCMC link that you posted.
So that's just a general website for the workshop. And if you go there, you find them under slides, and I'm gonna also send you if you want to look at the code, I'm gonna send you the link to the GitHub repo with the code of the slides as well. They are under the slides folder.
We do have one question, really a quick one. Could we introduce correlated predictors in a Bayesian model? Like what, I suppose what happens
that's exactly the same problem that you would have with the frequency linear model. When the predictors are correlated with each other, then you stumble across multicollinearity, which is an issue, and the Bayesian model per se will not solve that. You would have to solve it. So yeah, it's just, unfortunately, multicollinearity is not solved by the model being Bayesian. That's unfortunately not the case.
And my question, a very quick one, is in frequentist models, there's a lot of, people always tend to get z-scores of a lot of the continuous predictors, and doing standardized and scaling. I'm talking more about the predictors rather than the outcome variable, which you might want to have a log normal or whatever, right? Is there any, and this is supposed to have an advantage computationally as well, right? For the frequent, like sometimes the model will shout at you and say, please scale everything so we have it on the save. But is there any advantage for Bayesian models? Like, of course, like there might be an interpretability advantage, but I'm talking more like, is there an advantage in terms of like computing the model?
Yes. So yeah, standardizing, well, Z-scoring continuous predictors will definitely help the model converge, basically, but it's very unpredictable in the sense that sometimes it works better, but not faster. So, it just gives you a more robust answer, meaning that if you try running the model again and again, you get more or less the same answer. Just because the model is exploring a more restricted parameter space, but it doesn't mean that it takes less time. So yes, you get basically, you could get some benefits in helping the model converge, especially if you have continuous predictors that are on very, very different scales. So whatever applies to, to frequentist linear models sometimes also applies to Bayesian linear models in that sense. So yes, if you can Z-score your continuous predictors, it's a good way to do it. For the outcome variable, I tend not to transform the outcome variable or response, but rather to use an appropriate family distribution in the model.
Yeah.
The nice thing about BRM is that it's not like LM or LMER that you have to use LM or GLM. You can just use BRM and you can specify any family, and there are plenty. There's also the X-Gaussian family, which is good for reaction times, in fact. But that opens up a lot of cans of worms, so I'm not going to go there necessarily. But yes, you can do that as well.
Thank you.
I'm really sorry. I need to run. I'm
absolutely.
Because I have office hours, of course, because I'm very clever and I booked my office hours. I, made my office hours just straight after the workshop.
Thank you so much.
Yes, no problem at all. And I'll see you all tomorrow.
Same time as today.
We're going to talk about priors. Yeah. All right.
Thank you so much, Stefano. All right. See you tomorrow.
Bye.
See you, everyone.